I'm pleased to introduce Dr. Alice-Agnes Gabriel. She's an associate professor in the Institute of Geophysics and Planetary Physics at the Scripps Institution of Oceanography, our world-renowned SIO. She is also a guest professor at the Department of Earth and Environmental Sciences at Ludwig-Maximilians-University in Munich, Germany. She is a seismologist, combining simulations, which routinely use some of the largest supercomputers worldwide, with data-driven techniques and theoretical analysis to tackle one of the grand challenges of seismology, uncovering the physical mechanisms relevant to understanding earthquakes, which is necessary to then predict, to remediate, and to respond. Her research interests include earthquake physics, fracture mechanics, seismic wave propagation, and modeling of earthquake cycles and tsunami generation. She is the recipient of the 2023 Macelwane Award and was named a Fellow of the American Geophysical Union. She also received the 2020 Charles F. Richter, remember the Richter scale, Early Career Award of the Seismological Society of America, and the Ada Lovelace Award for High Performance Computing, and she serves as the current president of the EGU Seismology Division. Today, she will be speaking on cracking the earthquake code with machine learning, artificial intelligence, and supercomputing. Please join me in welcoming Dr. Gabriel.
All right. I will take you to the world beneath our feet, which is, especially in California, a dynamic puzzle of tectonic forces, of geological faults, and of earthquakes. And we are using supercomputers and ML/AI to start to decode this really complicated puzzle. What you're seeing just here is arguably one of the most beautiful supercomputers worldwide. This is Mare Nostrum, which is hosted in a previous chapel in Barcelona, Spain. And what you're looking at are a bit more than 150,000 cores that can be used simultaneously in parallel to solve problems like this one that you see animated here. So these are 15 terabytes of data. This is the output of an earthquake simulation that I will talk a little bit more about later. These are two earthquakes rupturing the same fault system. Actually, that simulation used about 4 times the size of this supercomputer, a little bit of a larger one. So earthquake science, similar to medical science, is increasingly data-rich. We have machine learning enhanced seismic catalogs, such as the one that you're seeing here. Every of these colorful dots is a single earthquake, smaller events. The larger ones you see in form of these beach balls that tells us something about the direction of these earthquakes. And this seismicity that you see here is outlining how the fault system moved during the 2019 Ridgecrest earthquake in California. So this is a zoom in this region here. And what this shows us is just how complicated these geological structures are that are moving during a single earthquake sequence. So we don't only have ML-enhanced seismic catalogs, we also have space geodesy, so we can use satellites to measure with sub-millimeter precision what happens during and in between earthquakes. We have seismic array processing, we can use telecommunication cables, dark fiber as new seismological instruments, producing terabytes of data a day. And all of this data is basically showing us this is complicated. What works against us here is that the longest modern instrumental earthquake records only exist since less than 100 years. So this is a very young science in the quantitative sense. However, the recurrence intervals, so how often these large earthquakes happen, often are more than 100 of years. And the animation that you see here are different models using different data sets, seismic, geodetic, tsunami data of the same earthquake. So this is the magnitude 9 2011 Tohoku earthquake in Japan that caused a huge tsunami and a nuclear meltdown. These are 32 models. They're all published. They're all good. They're vastly different. The different colors show how much different regions of this fault moved during the earthquake. So warmer colors, more reddish colors, mean up to 50 meters of slip, which is what we call the displacement from one side of the tectonic plate towards the other, and they don't agree. And this is the best we have. This is one of the largest and best recorded earthquakes. These are 32 published models. They don't agree, which highlights this challenge of having non-unique results, opposing hypotheses, and data sets often being studied in isolation instead of being integrated. Now, as a seismologist, we have the textbook knowledge that the most useful thing that we could do, predict earthquakes, is actually what we're least able to do. And that statement is still true nowadays, even with supercomputing and with MLAI, but I will show you how we are at the moment getting closer to maybe rewriting our textbooks by using these technologies. We are also often reminded of this fact, and the most recent reminder was maybe last year's Kahramanmaraş, Turkey earthquakes in 2023. On this picture, you see a drone image of part of the fault surface expression of this earthquake. In total, this was 300 kilometers, just the first one, rupturing the surface. So this is double the distance from here to LA, and causing huge amounts of devastation, more than 53,000 fatalities. And actually, this was two earthquakes. The first one that you see imaged here, and a second one just happening 9 hours later on a neighboring fault system up here. So you can see in red outlined the first of these faults, and in blue the second one. And these two larger earthquakes happened just 9 hours apart. Obviously they're related, but we have no idea why, and we couldn't predict either the first nor the second earthquake. Why this is interesting is that none of these two earthquakes actually ruptured in a way that they're supposed to do. We do have a basic understanding of earthquakes. We have hazard maps, we can prepare for them, but these two actually didn't follow the rules that we've laid out for them. In addition, this whole fault system here is actually very similar to the San Andreas fault. That is our local fault system here, and especially the southern section, which starts in Palm Springs, the Salton Sea in this area, is known to be long overdue for its next major shakeup. So to be able to better understand these events has direct implications to be better prepared for the next big one in California. So just when these events happened, we had a paper published in Nature modeling the two largest earthquakes in California in the last 20 years, the Ridgecrest earthquakes, and we used supercomputers to find the link between these two events. So what's interesting, the animation that you're seeing here shows the waves and the velocities on these faults, is that these two earthquakes actually happened on the same fault system. Let me play this one too. And we were able to understand how the earthquake could jump from segment to segment and how we can explain the delay of 34 hours between these two events. I have to note that the rebuilding efforts were much simpler for this event, luckily. Much less, almost no fatalities, almost no damage. And that it did include some field work. The way that I do it, I had to go to the supercomputing center in Texas to get a large enough machine to run these simulations. Now we could use these workflows that we set up to uncover the unexpected physics behind the Turkey earthquakes. And I just show you quickly two highlights. This is a now simple animation which just shows the velocities during the first earthquakes of what we uncovered. We saw that for the first event, which was started on the small, innocent little splay fault here, and it actually is supposed to stop at this intersection. It's not supposed to branch out in this direction, and it's certainly not supposed to then branch out also in that direction and causing this much larger earthquake than was ever recorded in this area. And we confined a dynamic mechanism involving stresses being redistributed and unclamping of the fault system to explain this really unusual behavior. And this can be built now into making better assessments of the next earthquake we expect here. The second earthquake of this doublet, which you now see animated here, was also interesting because in one direction it propagated at a normal earthquake speed, but in the other direction it actually broke through the barrier of sound that earthquakes have. So this is very similar to an airplane going supersonic speeds and causing a supersonic boom. We sometimes hear this here. Earthquakes can also propagate faster than the speed of the seismic waves in the surrounding rock. They go super shear, and they cause a super shear boom, stacking up seismic waves, and then producing larger ground shaking in much further directions than the properly behaved earthquakes. And you're looking at these two examples, Ridgecrest and Turkey, we see that these faults talk to each other. We cannot just look at a single earthquake in isolation, but we really have to look into these full fault systems. So the animation here is showing one big fault producing magnitude 6 earthquake embedded in its damage zone, all of these little fractures. Each of them can produce an earthquake because earthquakes are being recorded across magnitudes of -4 to 9. So magnitudes, as you remember, the Richter scale, we have now better ways how to quantify that, but it's a similar concept to measure the size of those. So we can now put all of this knowledge together to better understand how earthquakes grow from a tiny fracture to a catastrophic event. And that example here is the Kaikoura earthquake in New Zealand, where you see this earthquake cascade connecting and jumping across all of these structures. I want to highlight this little text here at the bottom. This model here that you see that looks nice and simple actually required more than or almost 300,000 CPU hours on a supercomputer. So that translates, you could translate that into 5,000 pounds of CO2. That's almost me flying in between Munich and San Diego in terms of carbon footprint, or 4 barrels of oil equivalent. So these models are interesting. They're solving the right physics, but they're very expensive. And they produce a lot of data. So where we are standing now is that we can use the results of this data-intensive computations to construct MLAI models using only the low-dimensional information, which enable us to evaluate these scenarios instantaneously. And where we want to get with this is in this area here. We are aiming for hybrid models combining machine learning and physics. Another reason why we're really motivated to do this is that none of the existing supercomputing methods are actually efficient enough for earthquake early warning or for fully physics-based probabilistic hazard assessment, where we need to evaluate 10,000s of models. And the last example I would like to show you is recent work of my student, John Rikowski. You see 2 animations. These are earthquakes close to LA. This is actually the 1987 magnitude 5.7 earthquake that happened just underneath Los Angeles on a blind thrust fault. So that means this fault was not known before this earthquake happened. The first of these animations requires about 100 hours on a compute core, whereas this animation requires 2 milliseconds. So this is actually fast enough for earthquake early warning. And as you can see, the results are equally complicated. Waves are being trapped in the LA basin and resonating because of the basin structure, producing much longer shaking than if you would use a simple early warning model, which just has a concentric circle of a wave propagating through. So I would like to conclude by saying thank you for listening and coming out on a Saturday. And also that I wanted to show you that by combining and pushing really the boundaries of supercomputing, combined with the machine learning and data sciences, we can step-by-step unravel this mystery of earthquakes that happen every day. Every day we have earthquakes in California beneath our feet that also happen on other planets to unravel really these mysteries that we are unable to fully grasp at the moment. So thank you for your attention.